is 2.5 minutes. Yeah? It's just, I'll see you in a minute. 2.5 minutes later, the person will come. It's a relative concept. Time is relative. I think Einstein said this. Welcome, welcome. We'll be underway in just a moment. Reinforcement learning. We cannot get enough of it, can we? Come on in. It's an institution of higher education, so we must reinforce our learning every time we get a chance. Did everyone get one of these? Do you love it? Yeah? Well, what's your favorite card? Which one? Molecular disruptor? Oh, okay, sorry. My hearing is not very good. So everyone's got your favorite cards, and maybe you could trade them later. That would be nice. So this is, we want this to be an interactive session. So welcome, everyone. So it's reinforcement learning, and we have two great speakers, but the speakers want to speak with you. So they've asked me to stay in the game. I've got the catch box, and you can ask questions and make this a dialogue so we get the energy high and that you come away really getting the answers to the questions that you're coming into the room with. So my new friend, Elise van der Poel, and she's like, that's terrible, but I do my best, a senior researcher at Microsoft, and at Microsoft Research. I mean, how cool is that? And you're a graduate of this lovely institution here. So it's a bit of a homecoming for Elise. So please give a warm round of applause for Elise.
All right. Can you all hear me all right? Great. Okay. Indeed, my name is Elise van der Poel. Before we get started, I want to set your expectations correctly. I don't have any chemistry training, so I hope you will forgive me if I say anything ignorant on that side. But I am a computer scientist by training, so I will very much come into this talk from the computer science perspective. I hope that's all right with you. Before I get started, I would like to get kind of a roll call. Who here has more of a chemistry background and who here has more computer science background? So who's more from the chemistry side? All right, and the computer scientist?
50-50.
Pretty good, yeah, pretty good. I'm pretty happy with that. All right, so let's get started. I want to talk today a little bit about reinforcement learning. That's learning from trial and error. But because I want to make it relevant to what you guys are also interested in, I'm going to use this running example of how you design a synthesizable molecule with very specific properties. That's not because I'm an expert on molecule design, but because it's such a nice example to go through. And to motivate a little bit the reinforcement learning perspective, or the machine learning perspective in general, as I've learned from some very talented computational chemists that I'm working with at Microsoft, there's a lot of human bias in how drug design is usually done. This might be a good moment to interject if you don't agree with that. Wow, okay. We're all in agreement. So one example of such a bias is Lipinski's rule of 5. Confusingly, that's 4 rules, but they all have the number 5 somewhere in the rules. And the idea of this rule is that they will, a lot of drugs that are, I think, useful for treating certain diseases obey this rule. Now, it makes sense to do something like this if you're a human. You're like a chemist in a lab and you want to design a new drug. You want some rules of thumb because the space of possible molecules is very big. The issue comes when you try to automate that or scale that up. You might automate this by encoding rules and heuristics like this into your algorithms, which works reasonably well. You can search this space much faster if you do it that way. But it also limits the options, the types of molecules that you can actually design. Another approach, and that's what I would do as a computer scientist, is to do fully unstructured design, where you just throw edges and atoms into 3D space at random and see what comes out. But apparently this generates a lot of nonsense that's completely useless, so it's also kind of a waste of time. Now, as I've said, biases and constraints make a lot of sense if you have limited resources available. They speed up search. So the space of feasible molecules is very large. And by using something like Lipinski's rule of 5, you've significantly reduced the space that you're going to search through. You're only going to search through the molecules that obey this rule. However, it turns out that only about 50% of drugs that are actually on the market obey the Lipinski's rule of 5. What that means is that if you constrain your computer algorithm to only search through this smaller space, you might miss some really good solutions. Now, this brings me to the bidder lesson. Who of you are already familiar with the bidder lesson? Okay, not so much. So this is an essay that came out a few years ago, written by Richard Sutton. That's the guy who wrote kind of the introductory textbook to reinforcement learning. And he basically makes the argument that time and time what we've seen as machine learning people is that methods that scale with and leverage data and compute will prevail over things that encode human biases and intuition. We've seen this, for example, in computer vision. We used to use SIFT features, which are kind of manually designed. And now we just throw a lot of data into very big models, and we get super nice results. I'm sure you've all seen the really nice AI-generated images that are coming out. We've seen similar things in chess, in Go, and also, of course, in language modeling, which I'm sure you're all familiar with. Now, the reason why we say this lesson is bitter is because we also like to sit down and think about problems and encode smart solutions to reduce our search spaces. But unfortunately, once you start throwing computers and more computers at it, these super nice, fancy solutions tend to get beaten. Any thoughts on this? No? You're all 100% in agreement with all I'm saying? Oh, that's great.
Here we go.
So in principle, yes, I agree. But what if you don't have so much data that you that the AI will figure it out by itself, so that you don't need to put any biases anymore?
It's a good question.
And especially in chemistry, we often don't have that much data.
I feel like you could have come here and given the rest of my talk for me, because this is exactly where I'm going to go. No, that's all right. That's a good introduction, that we've seen the same issues here. So if we would like to leverage, indeed, the bitter lesson for molecular design, we might want to train a generative model. So that's a model that we can sample molecules from. Ideally, we would be able to condition it, say, okay, I want you to generate some molecules, given that I want them to have this specific property, and I also want them to be synthesizable. Because if the molecules I'm designing are not synthesizable, what's the point? And we might have some data set that's some subset of all possible molecules. And if our model is big enough and we're good enough at actually training it, we would be pretty good at generating molecules from this data set. However, machine learning models, by design, so this is not a bug, this is a feature, only learn what's in the data. So as a computer vision example, if we're looking at all possible real-world scenarios, we might have a very large subset of that as our training data. Within our training data, we might have two labels, just as an example, that we want to predict. We have doctors, that we usually see in the context of hospitals and doctors' offices. And we have horses, which we usually see in the context of barns and fields. Now, that's great. We train this. It works super well. But then at inference time, or once we start deploying this in a real-world setting, we might encounter test data that looks quite similar, but is subtly somehow different. For example, we might see doctors who are doing house calls for farmers, or we might see horses who are going to the vet. Unfortunately, because machine learning models are kind of, most of the time, correlation machines, in this case, the horse would get classified as a doctor, and the doctor would get classified as a horse because of the context clues. But again, this is not a bug, this is a feature. So if we are going to learn molecular design from data, we might set it up in a kind of a similar way. We have the space of all possible molecules, and we want to generate molecules with a specific property. So some smaller set has the property, and the rest does not have the property. Then there's also a set of molecules that we don't know how to synthesize. And we also want to make sure that we know what synthesizable molecules look like and what non-synthesizable molecules look like. So our ideal data set would look a little bit like this. It has a nice coverage of all the different things that we care about. And while it's not exactly the same data distribution as the real set, is reasonably close. However, as Bernd also brought up, in reality, the data sets that we more realistically have are biased by the way chemists do research. And the way chemists do research is also biased by their heuristics and intuitions and experience. So it's very likely that the only molecules that we have in our data set are synthesizable molecules. Additionally, maybe all of the molecules that we're looking at have the property that we care about because we're just fitting to what we've already seen, which gives us not a lot of information about what actually causes this property. So there's no pattern that we can really learn from. And also we might have, let's say we're designing a drug for a new disease, we might have no examples at all of molecules that have this property. So what do we do then?
What I look at the balancing, trying to balance them up. I don't know if that's what you mean, but if you have data sets that are not equally distributed, you could address them by balancing during your train and test methods, and in that way you make sure that it learns instances in an equal manner. But maybe you have at Microsoft you do other things.
Yeah, I mean, data set rebalancing or like reweighting, that could be definitely an option if you do have some examples of your property. But there might definitely be cases where you're trying to find a molecule that has certain properties that you just don't have examples for yet. Which, as I understand, can definitely come up in drug design. But please correct me if that's not true. All right. Okay, so if our data set covers only a small part of all that's feasible, one thing we could do is set up a propose and evaluate loop. So instead of only looking at the data that we already have, we might write a computer program that proposes molecules and then use some kind of scoring function to evaluate them. So that's the microscope. This might either be a simulation that we would run it in, or we could even consider roping in actual lab experiments. We use this score then to evaluate whether or not the molecule has a property. And this way we can slowly start expanding our data sets so that it has more samples of things that we haven't seen before. And this way we can hopefully leverage the bitter lesson by increasingly covering the space of all molecules. Ideally, we would just throw an infinitely sized data center at it to search through this and generate new data for us, using just normal computational chemistry simulators. Now, this brings me to the basic reinforcement learning loop. Who here knows already a little bit about reinforcement learning? Okay, very nice. Okay, I'm also not going super deep into it. Maybe Mike will go a little bit deeper. Okay, but this is not a lecture. This is just to get everyone on the same page. So in a basic reinforcement learning loop, we have some agent, which I've represented here as a robot. The agent takes some kind of action in an environment. And in response to the action that the agent takes, the environment changes in some way. That changes the state that the environment is in. Additionally, we also have a function that we use to compute a feedback signal about how happy we are with the current state of the world. This is what we call the reward. Now, based on the observation of the state, the agent uses its policy to produce a new action that it then also takes in the world. So policy is a function that maps states to actions. This can be deterministically or stochastically. So the goal of reinforcement learning is just to find a policy that maximizes the cumulative reward over time. So If we go over this loop again and again and we sum all the rewards together, that's something that we want to maximize. So if we go back to our propose and evaluate loop, this is already very similar to a reinforcement learning setup. The only difference is that in reinforcement learning, we're now going to use the scores that the evaluation function produced in order to improve our proposal function or policy. One area where you might have already seen this is people train a generative model to generate molecules, for example, on a data set like C. And then on top of that, they use reinforcement learning to further fine-tune the proposals from the generative model. Any thoughts so far? Yes.
Thank you. I think I agree with everything you've said, but I see the problem a little different in the sense of that everything you've proposed so far is computational. Mm-hmm. And in a way, you're throwing compute at the problem, and then you're generating your scores or your policy by throwing more compute at it. And I think even if you do that, in the space that you're looking at, this is still a drop on the hot stone. Okay. And especially if you go to experiments in the other room, I think if you get up to 1,000, that's already a good start. But I'm wondering how far that can get you in a nutshell.
Mm-hmm. The computational evaluations? Or?
Well, on the one hand, reinforcement learning, which from my understanding is very data intensive and compute intensive, but then you don't have a way to make experimental data, but computational data. And at the end of the day, you want a drug or something that actually works. Mm-hmm. So where does that, in a way, fit in? Do you think you can, with just computational techniques, get there?
Actually, I don't think you can get there with only computational techniques. There's, for those who are familiar with robotics, the sim-to-real gap from simulation to science looks to me very big. Mm-hmm. So in robotics, if you learn in simulation, you then map it to a real version of the same thing. Whereas if you're simulating things in silico for chemistry, you cannot really go to the real thing. All you can do is do a lab experiment, which is very often quite different, right? So at some point, you're going to need to loop in some real experiments. The question is, if we leverage enough compute, can we make our filtering of what we actually send to the lab so good that we're saving a ton of time on lab work?
Excellent.
Yeah, back on board? Awesome. Nice.
Somebody else? Yeah.
Yes, I had a question about illustration you have with actually the path to discovering other data sets that you not have discovered yet. It's conceptual. I wonder then about the dimensionality, or like the general question, how many dimensions is enough to have a function that you can optimize to a certain parameter, or you reward, you said. So can you comment on something like the dimensionality?
Yeah, of course, these problems are super high dimensional, and that's definitely something that's very hard to work with. And I think that's why it's even more important to leverage machine learning methods here. I think this is stuff you cannot search through this exhaustively, right? You need something, as we say in machine learning, like amortized. So you want to use what you've learned from your failures in order to get better at searching this space. You might want to do some representation learning to reduce the dimensionality of the space. Something. I don't know what the actual exact answer is, but I think you won't get there without machine learning. Yeah. Does that answer your question, or have I answered a different question?
It's indeed part of my, indeed an answer to my question. My follow-up question would be then, like we know from the physical laws that it can reduce already the dimensionality of what is possible. Then I wonder always if you, for the non-synthesizable molecules, for example, there's a reason why they are non-synthesizable. So would it make sense to include these in your data sets if you maybe have another approach to include the physical laws that you don't need to take the data set and have extra dimensions to account for?
So my perspective on this is that you want to include things that are maybe true laws of the universe, like symmetries or something, but you don't want to include things that are human biases and intuitions. Yeah. The problem, I think, but I'm no expert, with some of the, if including a lot of like actual what things look like on the quantum level or something, is that these things are very hard to compute. So if you want to actually include them, that costs you so much extra compute, while you might also get to similar performance by just approximating them. That's how I understand it. But.
Yeah, I agree. Yes, thanks.
Yep.
I thought there was one more up here.
Yeah.
Yes.
I wonder if it wouldn't be easier to first look at which properties will actually you will be able to find, because the quantum computing properties are still computed, but the experimental properties, there's definitely time and cost restraints on that. But you might also get a lot of data from, for example, easy experiments, like you make a molecule, you do an LCMS, and you get a certain retention time. That gives you data that's really hard to compute, like or compute or experiment, like binding to certain proteins. Do you also take those kind of things in account, that you don't have to optimize for the property itself, but like a secondary property first?
I'm not 100% sure if I understand you correctly, so please let me know if I'm answering the wrong question. I think the issue with optimizing for proxy objectives is also always that if you turn a kind of a proxy into your objective, then that's what you're going to optimize for. And what you see experimentally when you do reinforcement learning experiments, that it just starts doing something that's called reward hacking. So it starts becoming very good at creating something that has the proxy, but then it doesn't actually have the thing that you care about. But maybe that's not the question you were asking.
No, that's a fine answer, but maybe you can get orders of magnitude more data from the secondary properties. For example, LCMS is very easy to measure compared to real binding
in the lab,
data.
you mean, or
yeah, in the lab. Because
okay.
in the end, you have to go to, I think you always have to go back to the lab.
Yes, I agree. You always have to go back to the lab. There's also... you can use kind of data for proxies that are related but not quite what you want for the type of approach where you do like generative model pre-training and then fine-tuning, for example. So you would pre-train on this data that you say is easier to get, and then you can do RL fine-tuning for the actual property that you care about. Would that be a solution?
Yeah.
Okay.
Thank you.
Great. Oh, so, good catch. Yes? All right. But to also go a little bit to, you want certain things that you actually know are synthesizable. You can kind of sidestep the issue of learning what is and isn't synthesizable by constraining your action space in a specific way. I know this is going against what I said before about constraints, but it's very specific. What you can do is you can start with a known set of synthesizable molecules and building blocks. And then at every step, what you might do is propose a synthesis step. So say, okay, I'm going to take these things and put them together. I select a reaction. And then I retrieve the resulting molecule. I evaluate if it has the desired property. I add it to my set of molecules that I know how to synthesize. And then I use the feedback from my evaluation to improve my proposal function or policy still. What this does is it will only produce synthesizable molecules. It will reduce your search space somewhat by cutting out the space of non-synthesizable molecules. And if at some point new reactions are discovered or published, you can just add those to your action space and then also search over those. Thoughts? Yep.
So here you mentioned that you start with the known set of synthesizable molecule, propose a synthesis step and retrieve the result. How do you propose a synthesis step?
Maybe you should start, maybe synthesizable molecules is, maybe the jargon is wrong. Maybe it should be like the building blocks. So stuff that you can cheaply get off the shelf.
Yeah. And synthesis step is not always one step, right? It's multiple step, and if you are aware of the concept of chemical reaction networks, then you might also be aware of the incompleteness of chemical reaction networks. It's hard to propose a synthesis step.
Right, but you can do something like select a reaction that results in something, right? A set of product molecules.
Still incomplete.
Yeah, but it doesn't. Why does it matter that it's incomplete for what I'm proposing? Because you can always append it later, right, with the new information.
Okay, thank you.
I'm getting my exercise.
Yeah, clearly.
There we go.
That's a good squat you got going on. All right. So a final thing that I want to talk about is the balance of exploration and exploitation. So we want, as I understand in drug design and molecular design, we want some kind of diversity of solutions. We don't just want to predict the things that we already know are there. And this to me feels like a classic exploration-exploitation problem. So exploitation in reinforcement learning refers to maximizing reward given our current knowledge of what's going on. So in the case of drug design, that might be something as simple as proposing a molecule that already exists, that's already on the market. It's maybe not the best fit for what you're trying to do, but it's reasonable. Then exploration would be something like potentially sacrificing reward in order to improve your current knowledge so that you can in the end get a much bigger payoff. So in the molecular design setting, that would be something like, okay, I'm going to design a bunch of really silly molecules that maybe don't make sense. But in the process, I will learn a lot about which molecules do and do not make sense, leading me to discover now something that's actually very valuable. So I think this is a thrombosis drug, if I remember correctly. But it could also be, I don't know, whatever is still out there that we haven't found yet. That to me is very exciting about applying reinforcement learning in this space. So this is definitely not like a new idea. So there's a lot of examples already of using deep reinforcement learning methods in molecular design. So a bunch of those are the kind of reaction step prediction in order to search through a tree of synthesis routes, this kind of approach to make only synthesizable molecules. Others are more the approach where you pre-train a generative model to output molecules and then fine-tune with reinforcement learning. But you also have things where they put kind of iteratively atoms in 3D space in order to construct a molecule that way and then evaluate it. So to wrap up my part of the workshop, I talked a little bit about de novo molecular design from data. I also introduced a bitter lesson, which tells us that skill tends to beat out intuition if we throw enough skill and compute at the problem. However, model performance is limited by data quality, and the data quality in chemistry is not always exactly what we would want to leverage the bitter lesson. So reinforcement learning allows us kind of to move beyond the data set. So it's a sequential decision-making approach that allows you to also take the future into account. It inherently deals with novelty, which we call the exploration-exploitation trade-off. And importantly, it also learns from feedback. So if you have some bad proposals, you can learn from that and get better over time. However, the bitter lesson holds for reinforcement learning too. They are computationally intensive and they are data hungry. But if you throw more compute at them, the solutions will get better. Thank you.
Thank you, Elise, very much. And it was a sweet workshop. It was about a bitter lesson, but that was a sweet workshop. Thank you very much. I love that. So now, next up, Mike Preuss. Come on down. So Mike is associate professor of artificial intelligence and a gamer, like an Uber gamer, if I understand it. Is that the technical term, I think? So please welcome for the second half of our workshop, Mike! Round of applause.
Thank you. I'm not sure if I'm a gamer. Well, I play games, yeah, but I learned that most of the EU people actually do. And actually the majority of gamers, if you pronounce it like that, in the EU is female since about 2 or 3 years. It's fairly interesting. Is that a pointer, actually? Ah, cool. So you will don't know, can you still hear me? Yeah. Okay. You will probably wonder why I put this weird picture on there as an introduction. Anybody has an idea what this has to do with reinforcement learning? Nobody? As all the stuff that you do as a child, and some of that also later on, learning to do this is quite, let's say, it's quite a thing. It takes you some time. It takes a lot of experimentation. It doesn't work from the beginning. And I used to say that to my students, the hardest thing that you have ever learned with reinforcement learning is very likely you have learned to walk. And that took you about a year of experimentation. But we don't want to talk about reinforcement learning in the wild, but more about reinforcement learning on chemistry, right? Wow, it really works. Cool. I got a new gadget. Okay, I try to keep it short, but I have to add a little bit because you will probably expect that I come up with, let's say, very technical descriptions of reinforcement learning algorithms. I'm not doing that. I'm trying to see it rather from a high-level perspective. And one of my origins is this, actually, and you probably have never heard it, but this is one of the key experiments that brought up evolutionary computation. And it was actually done because the people who did it didn't believe in theory. So this is actually the design of a throughput nozzle for rocket science. It's actually rocket science, so it's something like very high temperature gases. And the theory at that time said that this is the ideal form of that nozzle. And the guy who was later on my PhD supervisor, this guy, Hans-Paul Schwefel, and two other people at that time, they didn't believe in that. So what did they do? They took this thing, this is 1.5 meters long, they cut it into pieces of rings of 1 centimeter, and they assembled it in new ways. And it's very similar actually to the algorithm that Elise has just, on one of the slides, has just presented. Where you take one ring out, you position it new, so you make a new step, then you measure it. If it's better, you keep it. If it's worse, you put it away, and you revert to the old thing. So that basically brought up evolutionary computation. This was the final result they got after 150 steps. It was far better than theory allowed. And if you talk to the people nowadays, they will tell you that, well, 15 years later on, theory actually kept up. So now theory also says this is optimal. Just saying. So my second route is actually in ChemAI. And we actually have a connection, Elise and me. I was wondering all the time, who's this Segler guy who is... and he actually took part in both of our lives in some sense. In mine, he dragged me into a paper project about real synthesis, and it was very funny, and I don't want to waste too much time now with telling the story, but basically he was looking for somebody who was working with Monte Carlo research. And he looked up the web on who is in that university in Münster in Germany where he was at that time, and the only guy who did some research and teaching in that area was me. Because I set up a course that shouldn't ever have been there. I set up a ChemAI course in information systems. People loved it. I loved it as well. So we did that and came up with some paper later on. I will show you very soon because I think that's probably the reason why I'm still somehow dealing with chemistry projects. I do a lot of other stuff as well. And I'm not really a reinforcement learning expert, I would say, but I'm applying reinforcement learning. I'm in a reinforcement learning group, but what is reinforcement learning? Good question. This is the setup for today, and this is probably the reason why people have invited me, and probably why people invite me all the time, because they think that I have some clue of chemistry, which I don't really have, but I'm not. Yeah, I have a bit, maybe. I was in school. But actually, I think many of the things that we are currently doing don't really need very, very, very deep expertise of one specific algorithm. They rather need some more thinking out of the box and applying things in new ways. And this whole thing, Marvin just had the idea to take the AlphaGo thing that was out there and apply it to chemistry, namely to retrosynthesis, and we made it fit, and it was published, as you can see. So I don't want to go into detail, but this is Monte Carlo tree search on one slide, and it has Monte Carlo in it, so it is fairly much random. That is important later on, because if it's getting too weird, it's going to random search, sort of. So the whole idea is that you don't go through a whole tree, that we've seen the pictures already with Deep Blue, where basically the idea is to go through the whole search tree and find the best move. We give that up. Monte Carlo tree search, we know we can't do that. The tree is just too big. So we just follow the leads that we have already seen. And I don't want to waste too much time. We want to have some discussion, right? So one of the ideas that are contributed actually to this research is if we want to throw Monte Carlo tree search on it, then we put the end product of what we want to generate in the root, and we bring it down by applying reactions backwards to the things that we actually have from the shelf, and then we are done, sort of. And well, yeah, is that reinforcement learning? I mean, I had a discussion actually a few days ago with another professor in Leiden. We don't really know. We don't really know if it is sort of reinforcement learning. It is sort of not. So, well, I'll leave it like that. Thing is, of course, if you apply it to chemistry, the system is not so well defined and not so easy to handle and not so small as games. I mean, and if you think about chemistry problems, then even games like chess and Go are small, right? And well defined, actually. Okay, what's on the next slide? So that is something that we currently do. Well, I'm still dragged into chemistry projects all along, and we are asking now the question: what if we have multiple goals? So for the original retrosynthesis paper, the goal was only that we want to find at least one way to generate this thing. If it's good or bad or anything, we don't care. We want to find at least one way. And we did. But now if you have multiple goals, like, I mean, as I said, I'm not a chemist, so I'm a bit naive here. I just said, well, we want to get pollution down and maybe the cost of the materials down and stuff like that. That would be 2 goals. Well, you can even think of more goals like that. And then you have a problem, because if you have something that is multi-objective, and there's not much out in that direction actually in reinforcement learning, and people are doing it also on Monte Carlo tree search for multi-objective. I think there is, from the last 10 years, there's 4 papers. Now we write another one, so there will be 5 at some point. But I think you're still getting the point. It's really pretty unused. But actually, I have contact. I mean, I'm not doing only chemistry. I've been working with people in let's say, engine construction for ships, in automobile and whatsoever. And everybody from the practical side will tell you, like, I don't have 1 objective, I don't have 2 objectives, I have 35 objectives. So what am I doing now? Well, this is another discussion, and if you have 35 objectives, you're just lost, because we cannot do that, and there will be probably never a time when we can do it. I don't know. We can do 2 or 3 or 4, and everything else has to be a constraint. Just to explain, why do we want, I mean, only for the ones of you who are not, let's say, in multi-objective optimization or have never heard about what a Pareto front is. So if we have multiple objectives and they are partly contradictive, we have this red thing here. We call that a Pareto front. And that is actually, let's say, the line of ideal compromises that we can achieve. So all the solutions on this red line are actually compromises that are ideal. They cannot improve in one direction without losing on the other direction. So all these yellow, oh shit, I switched it off. Oh, cool. I just found another thing to press here. But I'm not using that thing. There's another button here. I don't know what will happen then. So you don't want to know about these yellow things because they're not ideal compromises. You want to find these red things here. Just saying. So currently we are just juggling around a bit with that. What you can do, so you don't have to understand any of this. The only difference that I want to show to you is this SO means single objective and MO means multi-objective. And we did the same thing, for example, here. It's basically the same thing with 3 objectives, and we did it in a single objective way, and we did it with a multi-objective way. And actually, for some objectives, multi-objective is better. Also here, don't want to go into the details, but if you have, how can you do it single objective? You may probably ask yourself, like, if I have multiple objectives, well, I just put them together and weight them somehow. If I don't know anything, just 50-50, and then I just find the solution that, let's say, comes up with the best value for this weighted. For this weighted approach. But if I do that, actually, I hide a lot of interesting solutions. So I can also switch it. So I can use the weightings and let's say start them from 1% to 99 and so on, go over the whole spectrum, and then everything that I generate, I put into the solution set, and then I evaluate it, and that's what we did here. So if we have SO here, that means there's not one algorithm run back there. There's a lot of algorithm runs with different weights, and still you cannot find everything that you can find with the multi-objective approach. Just saying. So that is what we do now at the moment. And now the question is, well, what does it have to do with reinforcement learning? And I sense I'm talking too much, right? We are not very interactive. But yeah, you have a question. There's a question over there.
Thank you. I was wondering about the multi-objective when you said you can't do 34 objectives. I get that it becomes harder and harder the more you add, but assuming you're just weighting them and adding them, maybe with different weights, and assuming somebody can figure out what they want, what speaks against doing it for, let's say, 10 properties that you optimize simultaneously?
One thing that gets really dramatic with a rising number of dimensions is the comparability of solutions. The problem is that the more objectives you have, the less the solutions are actually comparable. And I can't really go into the details now, but then you generate a ton of solutions of which only a tiny subset you can actually compare, and everything else is of the same quality. So that's a tremendous problem. So you would probably try to bring that down to something like 3, 4, 5. So I think 5 is the highest number that I heard people actually use in practice. And that already means that you generate a lot of stuff where you actually can't say anything about it. So it's basically, simple answer, curse of dimensions.
Thank you.
You're welcome. Okay, so we were about to understand what reinforcement learning is, or I was about to understand. Yeah, thank you. Actually, it's not so clear. Well, one thing that what we learned in the beginning, we have to have an agent. The agent wants to learn something, and then the agent does some exploration that gets some feedback from the world, tries to improve the behavior, and it means that somehow Monte Carlo tree search is also reinforcement learning, because we do that. We have some kind of model. Some people I know say that evolutionary algorithms are also reinforcement learning. I don't know. But what we need is actually basically the agent that can explore the world somehow. And we can somehow memorize what we get back from the world. And the striking thing, I think, or let's say if we think about possibilities how to apply reinforcement learning in the world, it's about processes, sequences, policies, right? It's not about standing still. It's not about the one configuration, basically. If you take any reinforcement or deep reinforcement learning algorithm from the shelf, it's always about policies. So you generate a number of steps that lead to some success. Interestingly, nowadays, I mean, there was reinforcement learning before. I don't know if you know the details, but basically you could do it table-based. Well, it's a little bit lame, and basically if you want to apply it on a huge system with many complexities, so big numbers, table-based doesn't work, so it's just too constrained. So I think we really made a step when we came up with deep learning models. I mean, we hardly understand what kind of, let's say, information organization they have, so how they memorize things, we don't know, but they memorize some things, so we can use that. And do we actually need the latest? Well, if we want to apply reinforcement learning, do we need to apply the latest algorithms? I don't know. I mean, I have a PhD student who is trying to do something that is, according to our chemists, difficult. Like he tries to do protein docking with moving ligands. That means you have the huge protein thingy that is very complex and big, and then you have the small molecule that could be a drug, for example, and it tries to somehow bind to the protein. And all we can do up to now is actually we can do the thing if everything is static. Like the protein doesn't move, the ligand doesn't move, so we go over the surface of the protein and try to find places to dock. And yeah, it has become much better in the past, so we can do much more stuff that we couldn't do before, but still we are pretty far from, I mean, it's very interesting for me to see as a computer scientist, we are pretty far from what we actually should be able to do, right? The protein is a 3D thing, it's moving around, and shouldn't we be able to somehow find a way to model this process of docking to a protein? But this is so complex that chemists don't even really think about it now. I think we are going to get there at some point. We are making progress. Yeah, the picture is macroscopic protein undocking. It's just for, if you don't want to listen to what I say, you can look at the picture at that time, and I found it a bit funny. Yeah, interesting also, that is on the top of the slide, one proof, for example, that the algorithm actually is not that important is that the paper that I showed you at the beginning that Marvin basically did, and I helped a bit, that has been redone more than 20 times now in different ways with all different kinds of algorithms. So is there a specific algorithm that rules? No, there's not. And we knew that. It's a lot about how you represent your information, how you put the problem into the algorithm. I think that's let's say that's the construction yard where we have to really do a lot of stuff in the next years. Whoop. Doesn't move? It does. Okay. So if we think about, because I said I'm coming from ChemAI, and we have these little games like chess and Go and stuff, and it has not been solved, by the way. If somebody tells you it has been solved, this is wrong. But we can generate AI policies that are playing better than almost every human that is in the world. So we have games, and we applied some kind of reinforcement learning on it. And we have, on the other hand, we have chemistry problems like retrosynthesis, and we applied something. What do you think, which tree stands for which problem class? Like, one of the trees is standing for the, let's say, the deep tree and the wide tree. So which one is which? What do you think? Who thinks that this is the chemistry tree? Okay, 2, 3, okay. So the others don't have an opinion, or?
That was more like 5.
There was five, but very.
Like this.
Okay. 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 Why do you think that?
I don't know what red would represent, but yeah, in the chemistry, it's very often that you have huge.
Oh, sorry. My fault.
It's soft.
Yes.
Yeah, it's just like, because I think in the chemistry you have very often those huge input spaces. So you have, but I don't know if the
No,
width,
that's a
my
good hint,
interpretation.
actually. You're fairly right. I mean, when I was coming, think of the situation when I was coming as a game researcher, I was drawn into this chemistry project, and people tell me, yeah, okay, we have a tree too. And on every level, I mean, in every single node, when you think when you think about the possibilities, like what can I apply here, and Marvin tells me like we have 43,000 possibilities here. What, in one node? Oh shit. Okay, that doesn't work. In games, I mean, think of Go. It's very limited, or of chess. You may have something like 20, 30, 40 possibilities. That is what that tree means, right? You go down from a root, you start somewhere with one possible move, and in chess, I think you have something on the order of 10-ish for the start, so that you have 10 nodes on the second layer. And then from each of these 10 nodes, you have something like 10 or 20 decisions. But in chemistry, we have thousands per move. And actually, in Monte Carlo tree search applied to games, very often we have game lengths of, give me a second. We have game lengths of something like 1,000 moves. Well, not for every game. I mean, chess is shorter, I agree. But in chemistry, we have game lengths of something like 10, and then the chemist will tell you, no, I'm never going to synthesize that. If it's 10 reactions, give me something with 3. Well, okay, that's what I mean here. We have a much, much different tree. So the tree has not that length. Basically, we are doing only a few steps, let's say 10. But for each step we do, we have thousands of possibilities. And when we are doing games, we have many more decisions, but for each of the decisions, we have only a limited set of possibilities. Let's say 10, 20, maybe 100. That's already quite a lot. So now we come you with your question.
So I didn't quite catch the distinction between physical moves and all the set of possible moves, because the set of possible moves per like molecule, assuming you don't know the physics, is going to be like 10 to the 5, right? So, but in terms of physical moves, I think there's only 50 or so. So there's a huge gap. Like, what are you defining as a physical reaction here? I know that sounds like a trivial question, but I think it's probably not.
Well, I'm just thinking out of the, let's say, system, how it was presented to me by Marvin. Let's say, the way we did this decision, to which we tried to understand which possibilities are there for a move, so which moves are actually possible. We tried to bring down the number from all available reactions that were recorded in order to which reactions would be applicable here.
And how do you do that? Yeah. Oh, and how do you do that?
Well, by preference learning, or let's say they applied a deep learning model, and that was there before already. So that was before we tried to connect all this. They had basically already solved that, sort of. Well, they had tackled that. But that doesn't really solve the problem, because what they did is they learned which of the reactions are actually more likely, which basically still gives you the whole catalog. Then you still have the whole catalog of several thousand reactions that are possible, but you know, or at least you have an estimation of what is more likely and what is less likely. And then you have to make a cut, because with something like 5,000 reactions or whatever, 40,000, Monte Carlo tree search is hopeless. That will not work. So we discussed that a bit. I think Marvin set the number 100 at that time. We cut at 100, which is probably as good as cutting at 50, 60, 70, or 200, or doesn't really matter. It just has to be a small number. And then everything else we ignore. It's still it's quite a huge tree, I would say.
Next one.
Yeah, but are you not then discarding quite a lot of information, right? Because if you assume that there are 40,000 reactions possible, and then you say all of a sudden, well, I only look at 100 reactions, right? How does that work?
Well, it still gives you enough possibilities to make almost everything. I mean, I don't know how I can nicely describe it, but the time you want to invest for getting anything reasonable out is limited, right? So if you want to go into the total enumeration thing, then it will not come back with a result at our lifetime. And that is something that we cannot use, right? So we have to make compromises. And I agree, it's somehow weird. But I have a physics in minor. I have a minor in physics, I wanted to say. Physics in minor. And I learned that very often, that's what physicists are bragging with, I think, that very often you have to just remove things that are in your way, that you have an equation of 20 things and you say, well, these 17 things don't play a real role here, so we just remove them. And then we have a nice equation of 3. That's basically what we also did there. I don't say it's the best way to do it, but it's a way that leads you to results. So yeah, I agree. It's a little bit weird, but it's a compromise. Compromise to get results in our lifetime. Do I have another slide? I think so. We have something like 5 minutes left, I think. What? Oh, there's a computer. Oh, cool.
You've seen one of these before, right?
Sorry for that. Okay. Yeah, I mean, we brought that up when we prepared the bitter lesson, and also I have some guy, I still have to do that discussion in our reinforcement learning group who thinks that the bitter lesson is really bitter. We still have to discuss that out. We're coming a little bit from the other side. You can, if you know that the most important problems that game AI people have been dealing with in the last years have been Go and then StarCraft and OpenAI 5 tackles Dota or whatever. So all that stuff. What we've seen is that DeepMind and other big tech players took away our fancy problems. They just sort of dealt with them and they are gone. And now what do we do? Because actually, we have only this. We are poor academic researchers, so we have only this intuition thing that we can use, and only big tech has the compute to actually do things. Well, I just want to put that in here. Actually, maybe it's a good thing that we can do that stuff, blow up these algorithms that are actually simple with a lot of compute and a lot of data, and make them useful. Actually, I don't think, but we had this discussion before about intelligence. I don't think that the things computers are really good in, so basically all that AI can ever do, I don't think that this is very much in line with human intelligence. It's very different from it. And maybe it's quite a good combination to put these two things together, like human intelligence and artificial intelligence. But we are running a little bit out of time, and I'm trying to get to the next slide. There are some more critical voices, right, about AI. So the last part is a little bit about my AI statement. And I'm not saying that I completely follow Gary Marcus in that, but he has a point. There are these funny, for example, completely self-driving taxis in San Francisco that ran into the concrete and got fixed there and stuff like that. So things happen. They are very funny, but don't solve our problems. And I think there are some issues where we don't have data, for example, and try to reason about things where we actually don't know, or we force the models, and we know that these models can't do that. All this deep learning stuff basically can only do interpolation in some sense, so it cannot extrapolate. So everything that is new, that is coming up, that has never been there, is basically not solvable or not trackable. There's this other guy. This book is recent. It looks very old, but this book is from last year, I think. I think he made it like this. So he also says, like, in the pandemic, for example, a lot of AI systems that were running in the US in the clinics had to switched off. Had to be switched off because they couldn't deal with the situation. Everything changed, and this has never been there before. This has not been in the data. The pandemic has not been in the data. So a lot of AI failed, actually. But here, RL could actually be good, because RL has this component of we are playing around with things and we are trying out things that we have never tried out before. I definitely totally agree. Supervision-based learning systems or supervised learning-based systems alone will not be the deal. And some things that may or may not happen to us, I don't know. Are you familiar with the term AGI? I guess so, right? Or at least an idea. Artificial General Intelligence. So the thing that assumes that